Hey guys, sorry about that. I took a break for a bit. As you guys can see, the time has moved forward. So we're in the morning now, 7:38 a.m. Let's get started. All right. So now we're gonna get to the script. Specifically, we're gonna get to the fish's controller. So we're gonna create a folder, call it scripts, and in that folder, we're going to create the C# script, fish controller. Okay. Let me make sure. Yep, FishController. So this is the my reference code right here. It's on my other screen. Yeah, I'm going to be referring back to that because I want the code to line up, and also I don't know everything by heart. I haven't looked at this in a while, so I just want to make sure I have everything right for you guys during this code along. Okay, and in the future, if you guys want a more detailed thing, of course, let me know. I'm really hoping people let me know. Okay, so that's that. You could double click on that to get your script up. Okay, I already have my Visual Studio Code open, and my script folder is right here. Fish controller is right here, and here's the start. So this is the bare bones starting point. We're going to add a public float. Well, let's first talk about it. So we're gonna first create a simple controller where the fish just moves forward, backwards, and turns left and right. Okay. Using this controller, we're going to then create a network that that gives us output, and then that output gets given to this controller for the movement instead of, let's say, our key output. Like if I press W, we get 1 as an output, and that gets put into the controller. But when you're using a neural network, the neural network gives you the 1 value or the -1 value that simulates W or S being pressed. Okay, so this is going to be more clear to you when it's written. Okay, we're going to have a float for acceleration and turning, and we're going to give it a range from -1F to 1F. So this is going to give us a slider in our Unity script when it's attached to the object. And I'll show you guys that in a second. But so we have our acceleration and our turning set up. Next, we're going to set up our function for the movement. So public void fish move. Move fish. Let me make sure that that's the right function from... I wanted to get the names right. Yep, MoveFish. Because I have to follow a convention, I'm going to be using this in different projects as well for my own personal projects. But this is cool. Like, I always thought making a neural network zombie game would be incredible, but obviously, like, there's just it won't be very good. But so that's an interesting concept. I hope someday, like, we get a very, very good learning zombie game. That would be incredible. Okay, so we have our MoveFish function, which is going to be called in the update function because update is called every frame. But we don't want just update. We want a fixed update because we want a constant update length. Okay, so the time it takes between updates, we want that time to be constant. So within the fixed update, we call MoveFish, and we pass it the acceleration and the turning, which right now is a public variable, so we'll change it in the while the game is running in the Unity editor. So MoveFish. Now, when we do the movement, this is where the movement is actually going to be done. We're going to be creating a vector 3 called input, and we're going to be storing a lerp position in the vertical direction, so forward or backwards, whatever, but we're gonna get a position in the forward or backward based on the vector. You guys will see. 3.lerp. Now we want to give it a 0 because we want to only move it on the forward, and so forward and backwards. Multiply that by 2f because that is the numbers that I'm using on my test project. This obviously you could put into a variable and just play around with it, and that way you'll get different like speeds of movement. But yeah, that's up to you. I'm leaving it at 2f, and then this is the starting position, right? So this is wherever the object is, wherever the agent is, wherever the fish is, and then this is the next position that we want the fish to move to. But this does not move the actual fish; it just gets the next position. Okay. You want that to be, and this is the it's a dampening, smoothing, but this is what makes it smoother, you know, and the step between, yeah. Man, curiosity. Okay, next our input is going to transform direction. We want the direction of where we're going. Input. So we get the proper direction from the input we get from the lerp. Okay. And then this is the line where the actual and that is going to be input. Yep. And then that's the rotation. Let's get rid of actual. Euler angles. Yep. So now we're gonna get the rotation from the new vector 3, in which direction we're rotating. And this is also going to be multiplied by the 90 to get the angle, and then the 0.1f. Right, so this looks good. This is for the movement, rotation. This is getting next position. Alright. And that looks good. Man. So close. Not close at all. So, didn't spell that right? Angels? It's early, and I haven't slept the whole night. Okay. Cut me a little slack for that. Apologies. Alright, but so that's everything for that. Hopefully you guys didn't make the silly mistakes I made. Euler angles, transform, and add this. Those were my mistakes, I believe. Okay. So fish. Now let's see you work. We're going to add the script to the fish. Okay. So like I was saying, the range, right, makes it to where we have a slider in the editor, which is right here. The slider goes between -1 and 1. And interesting enough, when you press W all the way, your forward movement on your axis, I believe, in your inputs. And your axis is here, right? You have horizontal and vertical. When you press W, your vertical ends up being 1. And like as you take your finger out, it goes from like 1, 0.8, 0.6, 0.4, and down to 0. And then when you press S, it goes the opposite way, so to -1. And when you slowly let go, it goes down. So it's basically like a slider. So it goes within this range as well. And this range between -1 and 1F is also what we try to keep the network between. But that doesn't matter because it will train to the proper range. Like the network should ideally adapt, but you want to give it good input, right? So you could give it crazy input and it should still be able to adapt. So you shouldn't have to give it -1 and 1, but you sometimes still need it. You still want to have like clean data given in. Let's see if this is working properly now. As you can see, we have it's slightly up, so slightly moving up. We make it move up a little more, and it moves up more. So the slider controls its the acceleration slider controls its vertical movement, and then it starts turning with the horizontal movement. So the faster you go, the bigger turns you get, and the more you turn, the smaller turns you get. So turning a little bit, you get really big turns. And using this, you could basically cover everything in the map and get as much food in the future as you possibly can. So it's a good movement. It's a good way to move. And that's the movement for the fish, basically. And the movement is very simple. The hard part is the network and everything that's going to come. Alright, so we have the movement. I guess the next part would be to... I don't know if I want to work on the raycast next, or if I want to just start getting into the network right away. Because the raycast is another part of this that we're going to need, but we might want to get the network set up first so that we can see the raycast. It'll be easier to implement the raycast after we get all the hard work done. Okay. All right. So now let's get the... I also need to remember how we're going to set up the genetic manager. So what's going to happen is the genetic manager is going to spawn fishes, and it's going to connect a network to each fish. Well, it's going to store all the genomes and mutate the genomes, and then give the genomes to the networks of each fish, and then create the networks and the body for each generation. I don't know if none of that makes sense, probably, but I'm just thinking out loud right now. And the network manager will also tell the genome and the network itself how many input and output nodes there are to initiate. Okay, cool. Alright, so let's get started with the genome. Alright. We have Neat Genome right here. Now this is going to be a little bit more interesting because, like let's go back to the paper real quick. So the Neat Genome is going to be, you have the genome object, the overall object that holds the node genes and the connection genes. So let's get started by creating node genes and connection genes. So right here, we're not going to need any of this, and we're also not going to need mono behavior. I don't believe... I don't even think we need any of that. So, but I'm going to leave that for now, and I'll take it out once everything is written. I don't want to deal with any random errors while writing. I shouldn't need that without maybe just whatever. Okay, so we're going to write another class, call it node gene. Okay. So as you can see in the where is it? The paper, we have node like ID basically, right? And we have a type, which is either sensor, output, or hidden. So that we're gonna have those same things in our node object. And we're gonna make all these public because I don't want to set up stuff, and my Visual Studio isn't really working right now. So for giving the types, we're going to use an enum. Input, output, hidden. And so those are going to be our different nodes that we can have. The input nodes are going to get the reference, going to get the information from our sensors. The output nodes are, well, the input nodes are going to pass the information to the hidden nodes. The hidden nodes are going to feed forward that information to the output node, and the output node is going to give that information to the fish controller. All right. So it's all a big circle, really. The fish controller gives the sensor information. The network gives output information, movement information to the fish controller. That then in the next update frame repeats the cycle, gives the next input information, and the cycle continues, and the cycle continues, and that simulates movement. And the coolest thing is just through this process of really it's just a frame and an object that's moving like a step forward, and then trying to understand what to do next. But through that we get some really cool behaviors. But let's actually get to making it instead of talking about it. Type. So this we're gonna have a oh, this should be public. And this is, so we have another variable of the type, and it's going to be type. Nope. Type. Yes. Good IDE. Good lightweight IDE. Good editor. Alright, give me 1 second. Just had to scratch my leg. Okay, now that that's done, we have to make a constructor for this. And our constructor is going to be, so that the ID that we get and the type. And type equals given type, and there we go. So whenever we create a node, we just give it a type and the next ID, and yeah, that's all it is. Next, we're going to create the connection gene. So the edge. Let's go back to the paper. Now, this is where more interesting things are happening. We have an int for the input, an int for the output, float for the weight, bool for the is enabled, and another integer for the innovation number. So let's get that set up. So we're going to do another class. I'm going to call it con gene, because I'm not going to type connection all the time. I should call it s gene. Alright, con gene it is. Okay, now we have a public int input node, public int output node, public float weight, public float, no, public bool, what was it? Crap, let me see the paper. Oh, I could just look over here. I'll look at the paper. Just enabled? What do I call it? Is active. Public bool is active, and public int enov num. Alright, let me make sure that this matches with my reference. Input, output, weight is active. I spelled out innovation number, but I'm not doing that here. Okay, so that's done. Now let's make the constructor. public like not scratch my chin. Congene int inNode int outNode float way bool active and int in node, and then input node equals in node. Oh no. And we're basically just setting it up to so all of these equal all these. Alright, so that's done, and I believe that that's everything for our connection gene and our input. Yep. And now we will move into the Neat Genome. So our Neat Genome, let me go up in my reference just to make sure everything's lined up. This is where a lot of magic is happening. But let's see what's going on. So in our Neat Genome, we have we take a public list of node genes. We're gonna call it node gene. Public list of node gene. I'm gonna call it node genes. And we're gonna do a public list of congene and call it con genes. Simple. Now we create a constructor. We're going to take an empty constructor and we're going to do an override constructor. Oh no, we're not. Okay, genome. So it's just going to be an empty one. We're just gonna initiate it. I just create the list. That should be count case. Alright, we initiate both of them, and then so in this, we're not always going to have a set number of node genes and a set number of con genes. So that's why we don't initiate them with a given list. We actually add them. And then be it through the mutations, right? Or through initiation of the network. So now in here, we have to create functions so that we can add them, but we don't actually we don't have to do that since these are public. So all we have to do is when we're calling the addition, we just do node genes dot add the node genes, right? But that's a little confusing. So sometimes I want to make this private. I'm thinking about making this private and just creating a function just for the adding of the genes, because we don't ever actually want to like set or get the node genes or the con genes. We don't really need to do that. I'm just looking through here to see if there's any real reason for me to do like a set on the overall node genes. Like if I want to ever initiate it with a given like number of input and output nodes, like a given list of node genes and con genes, instead of doing it one by one, adding to the input and output nodes. All right, I don't really see a reason why I should leave these public, but I'm still going to, because in the future I might need to access it, and I don't want to create extra functions, and this is going to become too dirty. But if I don't have to do that, I might make it private and create the add node. If it becomes confusing, we'll see how it goes. Right now, we'll leave it like this. And by I know like this is confusing, but trust me, after we get deeper into this, after we get the it's going to get a little bit more confusing. Just hang in there. I'm gonna drink some water, so bear with me for this. All right. Okay. So we have the node G's, we have the con genes. I think we're gonna leave it at that for now, and we're going to try to create an empty network. Right. So right now, when we create the Neat Genome, it's going to just be empty list. Then when we're gonna fill those empty list of node genes and con genes using the genetic manager. All right. We're gonna save this for now, and then we're going to move on to the network, I believe.